We need to talk about stable. And I'm not talking about you and your academic career. Okay? What we need to talk about stability is with alkenes. Now, if you're taking this organic class in the summer at an accelerated rate, then you probably do not feel very stable at this point. It seems like it may be in the beginning the gears turned a little bit because it was review and you're like, I got this. And now all of a sudden, bam, bam, 1-2 punch. I give you nomenclature of alkanes and then I give you nomenclature of alkenes and we keep trucking. And then I'm just kind of waving at you in the back window and I'm saying, bye-bye, come on, catch up with us. Well, that's just the nature of a summer class. If you're taking this during a regular semester, you might even feel the same way. All right? So your experience might be the same as someone in the summer. But here's the deal. We need to talk about stability. And I know that you are going to become very stable after this hump. This is kind of the initial shock of organic when people begin to get it. So bear with us. I told you very early on, put your seatbelt on and strap it tight because the ride is going to take off and it might sneak up on you. And maybe it has already snuck up on you and you're just now realizing it. But you will be okay. You will become very stable. So we need to talk about stability of the alkenes. All right, so double bond is the alkenes, and we can talk about stability. There is a trend that we can look at with organic molecules, and we can rank them like we've done before in the past. We can go through and say, listen, I think this is going to be more stable than this one, which is more stable than this one, and so forth. And this is how we do it. On these carbons that are sp2 carbons, look what I did there. I did a quick review on you, didn't I? sp2 because those carbons are double bonded. They are hybridized carbons. We know what that means. So on those sp2 carbons, we can improve the stability of those carbons. We can improve the stability of sp2 carbons in an alkene if we increase the number of groups that are on those carbons. All right, so what does that mean? What do I mean groups? All right, well, let's say hydrogen, 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 and hydrogen. This is how I want you to think about this. This carbon goes to the club or to the bar, and that carbon brings with it two buddies. Okay, those are hydrogens. And this carbon goes to the bar. And that carbon also brings with them two buddies. And let's say that these two carbons get into a fight. Well, I don't know what they're fighting over. You know, it could just be testosterone. And, you know, I don't want to be sexist. So it could be two women with their buddies that they're bringing to the bar as well. And maybe they're fighting over something and estrogen is taking over. It could go both ways. Who cares? But these two carbons get into a fight. Well, the way I want you to see this is that the buddies that they have brought to the bar with them, they're wimps. If you've ever seen the Andy Griffin show, this is kind of like Barney, okay? They're really skinny. They can't put up too much of a fight. You know, they've never lifted anything heavier than maybe a beer or a soda can in their life. So they're not going to do too much as far as taking up for their buddy. They can't take up for the carbon that's sp2. So what I like to say here are that these carbons are very exposed. So if other people want to come in and join the fight between those two sp2 carbons, they could. They could easily do it. And that's because hydrogen can't take up for it. Hydrogen can't take up for the sp2 carbon that's attached to. And those other groups know that. So they come in and they just take control and they can join the fight as well. Welcome to the world of organic. This is how I like to envision it, at least. I mean, to me, I think this makes sense. versus let's talk about the sp2 carbons on the hybridized model of the double bond of the alkenes, and let's talk about the electron density around those carbons with the hydrogens that are around it. Who wants to sit on that type of lecture? If you want to sit on that type of lecture, then you need to go to a university and take it there, not with me. This is not how I think about organic. All right, so the exposed carbons, because they're more exposed, the stability goes down. That's because other big loppy things can come in and attack those sp2 carbons, and the hydrogens, the buddies, can't take up for those carbons. So the hydrogens just say, okay, whatever, I'm out of here, peace, and away they go. But what if we switch one of the buddies, and we switch one of the buddies with some type of group? It could just simply be a CH3 group. Oh, now we're no longer dealing with Barneys from the Andy Griffin Show. Now we're actually dealing with somebody that maybe could put up a fight. In terms of a bodyguard, CH3 is going to do a much better job than hydrogen, and that's simply due to its size. This takes up space. And if it takes up space, then it can cover up this carbon a little bit better and have its back. So if these do get into a fight and another big clunky molecule comes in and says, bing, I'm going to go to that sp2 carbon, the CH3 group is going to say, no. Wait a minute. You're not going to do it here, because I can throw a punch and I can help fight you off. All right, well, if that's okay, then down here, if we can switch that hydrogen, and if we can put some type of clunky group on it as well, and this carbon can bring another type of buddy to the fight, then this big clunky thing is going to come in and say, I'm going to attack, and that CH3 says, oh, no, you're not. And the clunky molecule says, all right, fine, I'll just go somewhere else, and I'm going to swoop in through here. And this CH2 group takes up space, and it says, no, you're not. And the clunky molecule then has to travel all the way around to the other side of that molecule, and pew, right there it goes. Those hydrogens are not going to take up any type of fight or put up any type of defense. Hopefully you're seeing where I'm leading with this. What this means is that the more groups that you have around those carbons, the more stable that they become. In other words, if I have a version that has all hydrogen, and if I have a version that maybe has a CH3 group here and maybe a CH2, CH3 group there with some hydrogens. And then if I have a version that's got CH3 here and CH3 there and CH3 here and CH3 there, you look at the number of substituents, the groups other than hydrogens, and the more of them that they have, the more stable that they become. If there is a tie on the number, well, then we start looking at the sizes of them. Are certain groups bigger than other ones? If so, we need to factor this into our decision. So in the book, you're probably going to see an image that looks like this, and that is what that represents. Relative stabilities of alkyl substituted alkenes. Alkyl substituted means methyls, ethyls, propyls, so forth. We're not talking about alcohols. We're not talking about amines. We're not talking about ethers. We're not talking about halogens. All of those are set aside. We're only talking about the alkyl groups. Methyls, ethyls, propyls, butyls, isopropyls, sec-butyls, tert-butyls, right? Those are what we're talking about. So the most stable is going to be the version that has all 4 spots taken up by alkyl groups. And then if we remove one of those and switch it with a hydrogen, we still have 3. Those are pretty good bodyguards for the sp2 carbons that are involved in that double bond. It can still fight things off, but there's a weak spot. There's an Achilles heel. And if that begins to happen, the stability begins to go down. So this is ranked as number 2. All right, and then we replace it with 2, not just 1 hydrogen, and it's becoming more exposed. And a big clunky group can come in, and that clunky group can attack those sp2 carbons pretty easy, and we rank this as number 3. And then finally, if there's just one group, this is the least stable out of the bunch, and we're going to rank this as number 4. So the stabilities of the double bonds will first depend on the type and the number of those alkyl groups that are attached to the sp2 carbons. In other words, the carbons involved in the double bond. All right. Something else that's also going to play a factor as far as stability is concerned are cis and trans and E and Z. I've already really kind of sneakingly inserted this into our lecture, into a previous video, into a previous example. And cis and trans and E and Z will lead to stability because trans is going to be more stable than cis is going to be. I'll show you why in just a second. And then between E and Z, Z groups are on Z same side. This is kind of like cis, right? E is opposite. So E is going to be more stable than the Z form. I don't want groups on the same side if I could help it. All right, so why is this the case? We'll take a look at this image. Over to the left, you see the cis form, and over to the right, you see the trans form. Do you see what's happening? Here we have a methyl group, a CH3 group, point up to the left. And here we have a methyl group that points up to the right. These take up space, right? And I told you these were bodyguards. They're bodyguards for the sp2 carbon. However, if you look at this, one side of this is pretty well protected. If I get some kind of nasty group that comes in here and tries to ding, 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 attack those double bonded carbons, then these CH3 groups are going to brush it off, and it's going to say, no, you're not going to do that here. But if this molecule is pretty clever, all right, and if that big bulky group decides to come over on this side and attack, then it can, because this side is very exposed. That is why cis is not as stable as trans. Because on the trans side of the house, look at what begins to happen. Here we have one that points up, and here we have one that points down. These are bodyguards. So if a big bulky group comes in and decides to try to get into those sp2 carbons, well, there's a lot of space here that's taken up by the bodyguard. And it's going to have to kind of attack in the perfect position in order to get inside of there. And then if it decides to say, okay, I don't like that scenario, I'm going to go around here to the other side. My buddy had a better experience over there on that molecule when he flipped around. So over here, I'm going to come to the bottom, and it sees that that is also taken up as well. And it has to perfectly squeeze itself in there in order to get into those C or those sp2 carbons, those carbons that are double bonded. This is harder for it to do. It can do it. It can do it. Don't get me wrong. But it's harder for that process to happen. Because of that, trans is going to be more stable. And stability means it stays around longer. It doesn't crack, right? You're staying with me longer if you are more stable in this course. These molecules are more stable because they are staying around longer with their original intention. But once this other piece comes into play and begins to attack these carbons in the double bond, these could get destroyed. And no longer do we have what we assumed that we would start with. It's now something completely different. So stability is different than reactivity. And I need you to keep that in mind. That's a very important concept. Stability is different than reactivity. Stability means that that molecule stays around and it doesn't change. The higher stability that the molecule has, the lower the reaction. Because that means if a reaction happens, something new has to be formed. Okay, maybe you get a hint of where I'm going to go with this a little bit later. But this is a way that we will look at stability of alkenes. All right? If you take a look at this, here's another image. It kind of is a three-dimensional space-filling orbital that you see down at the bottom. And here you kind of look at the lopsidedness. Notice over here to the right-hand side, we see a group that points up and a group that points down. And we see that those groups do a pretty good job to nestle those CH or sp2 carbons double bonded here in the center. I think the space filling model shows this a little bit better than a sheet of paper would just stick some bonds. All right. Notice that no matter how I go around this sucker, that it's going to have a harder time to get into those double bonded carbons. Well, here in the middle, I see the CH3 groups that are both pointed down. Well, here they just pointed them up. They just flipped it around. That's all that they've done. So no big deal. It's the same thing. But I think this also clearly shows that on this side of the molecule, if I get a big clunky piece that tries to get in there and attack these carbons that are in those double bonds, it can't really do that well. But if it goes around the molecule and hits it from this side, then it could do that. And then over here to the left-hand side, the same kind of concept, except if I get a big clunky molecule that comes in, bing, it goes away if it attacks the left-hand side. But if it travels on the right-hand side, look at there, it can get right in there. It can get right in there to those sp2s and begin to do whatever it wants to do with them. So the question here, it says, is the stability correct the way that this is listed? Is this one greater than this one, which is greater than this one? Wrong. These all need to be flipped around, okay? And actually, to tell you the truth, out of these two, yeah, if each carbon has one substituent, it's a little bit better than if only one carbon has substituents and the other one's very exposed. But these are almost regarded as equivalent. Not quite, but we would almost look at these as one is as bad as the other. I mean, give me a break. One's exposed fully on the right-hand side. The other one's exposed fully on the top or the bottom. However, the middle one is slightly better than the one to the left. And the reason is because this sp2 carbon at least has one substituent, and this sp2 carbon has at least one substituent. Over here, this one's got two substituents, and this one doesn't have any at all. So it looks like this is a better sharing of those groups, and it gives itself a little bit more protection as far as both are concerned, and that's why we rank that one in the middle. But one is as bad as the other one is. All right, so let's do an example here. Rank the following molecules in order from the highest stability to the lowest stability. We have trans 3-hexene, cis 3-hexene, 1-hexene, and then cis 3,4-dimethyl 3-hexene. I'm going to have to draw each one of these structures out. Okay, that's what this is basically going to boil down to. Let's start with the first one, trans 3-hexene. All right, so I'm going to draw 3-hexene first. All right, 1, 2, 3, 4, 5, and 6. Spot number 3, 1, 2, 3, that's where I see the double bond. I need to draw the trans version of that. All right, so here are the carbons in that double bond. There we go. That's what we've just drawn. The carbon on the left has an ethyl group, CH3CH2, and then a hydrogen that points down. Over here on the right, we see this carbon that also has an ethyl group, CH2CH3, and then a hydrogen that points up for the fourth bond. There is the trans version of 3-hexene. Notice that the carbon to the left has one group and the carbon to the right has one group. All right, the cis form. Okay, let's do that. Bing, 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 bing. There we go. You missed those. I know you did. All right, and then we've got CH3, CH2 with a hydrogen, and then CH2, CH3 with a hydrogen. These are now on the same side. Okay. The next one, 1-hexene. Oh, that's a little bit different. 1, 2, 3, 4, 5, and 6. And this double bond happens on carbon number 1. All right, so here are the legs. Those are the carbons involved in the double bond. To the left-hand side, well, there's nothing really else attached to there, is there? There's 2 hydrogens, a hydrogen here and a hydrogen there. And then over on the right-hand side, I've got this 1, 2, 3, 4 carbon piece. All right, so CH2, 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 CH3. And then the 4th bond is not drawn, so it's understood to be a hydrogen. And then finally, this last one is a cis 3,4-dimethyl 3-hexene. All right, so I'm going to start with hexene first. 1, 2, 3, 4, 5, and 6. On carbon 3, I have a double bond. And then on carbon 3 and 4, so that's here and there, I have a methyl group on each one of those, dimethyl. So that's the way I'm going to draw that. And then it says the cis form. So the groups are on the same side. All right, so here's my double bond. Okay, there we go. To the left, I go up. There's a CH3, CH2 group. And then pointed down, I see a methyl group, CH3. Uh-oh. I did this on purpose. Look at that. This problem told me cis, but there is no hydrogen on that carbon to do that, is there? So cis is not appropriate here. I need a review again, right? That's one of the reasons I did it. So that cis is not good. This is wrong. It's a wrong term. And instead, I need to be using E or Z, not cis and trans. So cis means the same side. So that means that this really needs to be listed as a Z 3,4-dimethyl 3-hexene. All right, so now over here, this is my high priority group. And then over on the right-hand side, I'm seeing a methyl group, and I'm seeing an ethyl group as well. I need to make sure this is Z. So CH2, CH3, and then CH3. This is my high priority group. That's right there. So the groups are on Z same side, and there's our 4 choices. Whew, but we've not answered the question yet, have we? No, we've not answered that question yet. So I need to rank these in high stability to low. The more groups I have, the better off I'm going to be. All right, well, clearly, this is going to be number 1. All right, this is the highest stable out of the 4 choices. Why? Because this carbon has 2 groups on it, this carbon has 2 groups on it, and because they are completely covered, they are protected. So this is the highest stable out of the 4 choices. I then turn to the other 3. Well, this one only has 1 group on it. And the 2 here that we started with, the cis and the trans form, well, 1 has 1 group and 1 has another group. So there's more substituents over here than this one. That means this is going to be dead last. I know that already. That's going to be dead last out of the 4. There's only 1 group on there to protect, and that's it. So now I need to take a look at these 2. They have the same number of substituents, but here's the trick. We've already said trans is more stable than cis. That's because they're on opposite sides, and they're not really fully exposing one side or the other like the cis is doing. So the trans would be number 2, and the cis would be number 3. And there is our ranking in order from highest stability to the lowest stability. Take a look at your groups. How many groups are on those double bonded carbons? And that will help you make the decision of the stability order as far as the Blackboard questions go, the assignment questions on my test, and so forth. They will be this clear cut. We're not trying to trick you. We're not trying to make your life miserable. They will be this clear cut when they happen. We just want to make sure that you are taking away the overall ultimate goal of stability of alkenes when we ask these types of things. All right, so that's where I'm going to stop this video. In the next video, I think that's all we're going to talk about stability for now. But in the next video, we're going to dabble into a little bit of reactions. We've not really fully seen reactions yet. Other than the reaction between an acid and a base, we've not really talked anything else about reactions at this point. So before we do that, I want to give you some terminology and I want to give you some background. So that's what we're going to include here. I'm going to term them, I'm going to give you some background, and then fully in a different lecture module, we will focus entirely on reactions of double bonds. Yep, there's more to the story, and that's how organic is.